there's something you're still missing. Okay. Okay, so back to coupling mechanisms. Last lecture, we started looking at kind of issues with the supply in particular and how they arise because of package inductance and interconnect lead inductance. We looked at the fact that every package, for instance, every lead on the package has self-inductance and mutual inductance to neighboring leads, and that changing currents on these inductances produce what's kind of informally referred to as voltage bounce or voltage noise. Don't really call it a noise because it's not really noise, right? It's a deterministic waveform. But if there's lots of gate switching in a pseudo-random manner, the waveforms may in fact look somewhat random because there's so much activity, unpredictable activity at any given time. And some ways of combating that, we talked about differential circuits, kind of nice ways of designing your bond wires to eliminate these sources of problems, and also isolation in time. In a clock system, isolating the clock cycles where you do digital operations, let's say from analog operations, or from insensitive operations to sensitive operations, if you will. Now, we're going to go over all this again today, a little bit more detail. I won't talk about the power supply too much more. I think we covered that pretty well. Kind of the important issues we'll touch upon again. Let's look a little bit more detail at the source of the noise. So in a digital circuit, internally, you might be driving lots of capacitance, right? Or you might have some kind of external capacitance. So in this example here, can we zoom into just this picture? Thank you. So in this particular case, we're looking at a discharge of a large capacitance. And I want to emphasize this capacitance can be on-chip or it can be off-chip. And this large discharge current flows through this ground bond wire or lead inductance or package inductance, and that produces a voltage ripple on the local ground. And because I've got another gate here connected to this ground, let's say this gate is not supposed to transition during this cycle, but because of this voltage bounce, we may see a glitch waveform over here, and if we're so unlucky, that glitch could be captured by latch, and so we have an error in our system due to this voltage bounce. Now the dynamics of this are pretty simple. I have a voltage waveform that ramps downwards, and if I'm charging a capacitor, a ramping voltage, right, requires a constant current. So this is the current waveform. On the high to low transition, the current is positive. On the low to high transition, the current is negative. And because the bounce waveform is a derivative of this waveform, we can see that during the upward transition, we're going to get a spike in voltage in the upward direction, and then on the downward direction, a downward spike. And so this tells you kind of where, if you look at the waveform on these pins, you might see waveforms similar to this, and this kind of explains to you what's happening. It's during the rise time and the fall time that you get the glitches. Okay, questions? Well, don't only blame your digital circuits. You might actually have sources of noise coming from your analog circuits as well, and generally it's has to do with large currents. If you're driving large currents, large AC currents through your package, you're going to produce noise. In this particular example, you have let's say a two-stage amplifier that's driving a resistive load. This might be a DSL amplifier or a power amplifier or driving a microphone or anything that requires power. And it's drawing a large AC current through that load. It has to draw that current from the ground or from your supply, and that's going to produce now sinusoidal ripple on your ground. And so here, if I have another analog circuit that's trying to detect a weak signal, on its ground there's this sinusoidal variation, right? And that can couple to the input and compete with our input signal. So it's not just digital circuits that produce noise. Now, at the end of last lecture, we talked about one way to try to decouple noisy circuits from sensitive circuits. And so here you can see that I have two power supply domains. So I have a digital supply, which is presumably noisy because of all the switching activity. I have decoupling capacitors so that I'm drawing most of my noisy current from this coupling capacitor. This coupling capacitor can reduce the amount of bounce tremendously, because if I don't have this decoupling cap, why does the bounce go up? Let's just forget about the rest of the circuit. Let's just talk about the digital side. So the claim is if you put in this capacitor, the ripple goes down. Why is that? Okay.
Without that capacitor, it's drawing its current from off chip, and that's going to have a larger inductance.
Very good. Yeah. So the current then would have to come from here, and this inductance is even larger potentially than the, let's say, lead inductances of our board. So then the ripple would go up even higher. So this decoupling capacitor is very helpful. Last lecture we talked about, you have a separate analog supply, and it has its own decoupling capacitor, but ultimately, in many applications, you have to share the same supply, right? This might be the same battery. Your cell phone only has one battery. And so at some point, unfortunately, you have to connect these two things together. And if we just connect them without this inductor here, then this capacitor will also act like a decoupling capacitor, and it'll help draw, let's say, lower frequency current into the digital domain and increase the bounce on the analog supply. So the idea of this decoupling network is to put an inductor here so that now high frequency current only comes from this capacitor, and this current is mostly a DC current. Another thing that we mentioned last lecture was that this decoupling network better be low Q, right? Because if it's a high Q network, it's going to bounce. Every time you draw current from it, you're going to get ringing on this, and it's going to produce even more noise. So the way we do that is we could either put a resistor in series here, not so desirable because then we're just losing power to that resistor, or we use what's called a magnetic bead, which is a piece of magnetic material, a ferrite, that is lossy at high frequency. So the AC current sees loss that DQs the network, but the DC current doesn't even see the bead, and so you have no loss at DC. Okay, questions?
What's the size of that beam? Is it on chip or what?
The bead is off chip. Yeah, and it's a large inductor. It's yeah. Yes.
The inductor is off chip. How about connect the other side and instead of to digital VCC to the supply source? Make the two inductors kind of run parallel with each other. Yeah.
Yeah. You could do it that way as well. But because the supply has finite impedance at high frequency, there's still a path coming back, right? That's a very good question. I mean, that's, of course, a smarter thing to do. But as we talked about last lecture, at high frequencies, this is a regulator or even a battery would have finite impedance at high frequency. So we would try to decouple it for one thing. And this is also going to be far away, so this inductance is going to be pretty high, right? So this network is still going to be there, but it'll be actually, instead of putting down a physical inductor, you may end up just being able to use the leads, the traces, as your inductance. That's a great point. Thanks. Okay. Other questions? Okay. We also talked about where these parasitics come from, and for instance, in a low-cost packaging technology, we take our chip and we use bond wires to our leads. So this is a top view. This is kind of a side view, and it's exaggerated here. Of course, the chip is much smaller usually than our package. And so one thing that's important, and I want to emphasize, is that you'll hear a lot of people talk about the inductance of a bond wire. They'll say, oh yeah, a bond wire has 1 nanohenry of inductance. doesn't make really any sense. It only makes sense when you talk about a closed loop. So if you are talking about a bond wire, you have to define the path over which your current flows. So for instance, in some technologies, you may have a ground plane, and then let's say this is a VDD, this is a ground, and you want to talk about the inductance of VDD and ground. Then you could see that this cross section would define that inductance. And let's say you find out that in this particular technology there's 4 nanohenries in this loop. Then you could informally say, well, 1 nanohenry is due to this inductance, 1 nanohenry is due to this lead, and same over here, so you get 4 nanohenries. And if you want to make that concept more precise, you have to talk about what's called partial inductance. And it's something that I won't get into in this lecture, but if you're interested, come talk to me and we can talk about it. The important point is that here the current is flowing in this ground plane. That's why I define this loop in this following manner. Let's look at a couple other examples. So last lecture we said pin selection was very important. So let's zoom into this picture here. So in this picture here we see 2 attempts to bring in supply and ground into a chip. Someone who's experienced and someone who's maybe not so experienced. So in the inexperienced case, we could see that they've selected this pin for VDD and this pin for ground. And it's actually kind of funny because in the old days, you could buy chips that always had VDD and ground in these locations. And it's actually probably the worst choice for VDD and ground. And it was standardized in the industry. So every chip you got had VDD and ground here. And the reason it's a bad choice, as you can see, as I mentioned last lecture, first of all, what does ground mean, right? It's a very dangerous thing. It could mean that there's a wire trace on the board that connects these 2 points. It could mean these are vias down to the ground plane, and there's actually a ground plane. So if there is a ground plane, that's the case here I've drawn in red. I don't know if that shows up so well. But here's an amplifier, and I'm supplying VDD and ground to it. And of course I put in some local bypass capacitor. And then I want to know what the path is around the loop. So I go from here, go through this pin, go through the bond wires, come on chip, go through this bypass capacitor, come down through these leads, all the way to this ground connection here. And then this ground can either flow through the ground plane, maybe it would take this path, or if there's onboard traces, it might take this path. But you can see that in either case, there's a huge loop here, right? So in the case that it's on board, we're really screwed. We got this huge loop. In the case that it flows on the ground plane, it's a little bit better. It's more of a vertical inductor, right? So now the inductor is defined in this plane. In this case, it's defined in this plane. But why did we do that? I mean, if we had just used 2 adjacent pins for VDD and ground, you could see that the loop is very tiny, right? And now this loop has very little inductance compared to this huge loop here. Okay? Questions or comments about that? Well, not only do we have to be careful about supply, we also have to be careful about our I/O pins. Because why is it important to have low inductance on our I/O pins? Say you're designing an amplifier and you find out that you can have even 10 nanohenries of, let's say, source or load inductance, and the circuit still works fine. So is it okay to do something like this?
You may cause some interference to other signals, like mutual inductances and stuff.
Yeah, not only, it's a reciprocal thing, so not only do you potentially make interference for other circuits, you also pick up interference, right? So you're designing a good low frequency antenna, a static antenna. So this loop here, if there's considerable power going through this loop, probably wouldn't be on an input, it would be on the output. But equally well, this could be an output stage, then that's a source of interference. If it's a big loop on the input, it's a good sink for interference, if you will. It's a good way to pick up interference. And it's a problem because this interference signal could compete with your tiny signal here, right? Or even worse, it could totally swamp out your tiny signal, right? And saturate this amplifier. Remember, this amplifier potentially has a lot of gain. So that tiny little interference signal can totally saturate out your amplifier stage, and now your circuit just doesn't work. So of course, here's the dumb way of doing it, just like before. Here's the smart way of doing it. Use two adjacent pins, and now the loop is very small and you pick up less noise. So here's this loop versus this loop, depending on how the grounds are connected. Okay. What about this connection here? The way I learned about this connection was I was doing a summer internship, and I was designing a circuit, and it had lots of problems with the package. It was a power amplifier. And somebody told me, put two ground pins next to your input. So instead of having one ground, so this is plus, this is minus, they said put two grounds surrounding it. And I said, well, why does that help? I said, I don't know, but it just works. And so then I tried it, and yeah, it did work. It worked better. So then I sat down and thought about it, and it's a little bit subtle, but let's see what you guys think. Why would this be better than this?
Yeah, basically flux cancel out.
Very good. Yeah, this is the idea. It's a common mode cancellation technique. You have one loop in this direction, right? And then you have another loop. We use another color. Unfortunately, we just have black here. The other loop goes in this direction. And so it's almost like I have two loops here in opposite directions. One loop in this direction, one loop in this direction. So if I have interference coming in, a common mode interference, right, a magnetic field, let's say that's incident in this direction, these are the magnetic field lines going through, you can see that I pick up the flux in this direction and then in this direction. So it's like I pick it up with positive polarity and then with negative polarity. And if these two pins are close together, hopefully the source of interference doesn't change much on this scale. And so then I get much less pickup on my input. And it's actually really neat. You go from a common mode input, so you go from if you look at the noise on the input, it may go down from 10 millivolts down to a millivolt, in a power amplifier application. So it's a really cool way of getting rid of common mode noise. The other thing it does, of course, is now the input has two loops in parallel, right? And these two loops in parallel just have less inductance. So it has less inductance and it has less mutual pickup from other sources. Okay, questions? Okay, well, if you've done everything you can with your package and your board and you still have problems, at some point you have to go to some more advanced packaging technologies. And there's a couple of good solutions. One way to reduce the length of your bond wires and therefore to cut down the inductance is to use a package that has actually what some people call an exposed paddle. And the idea is that if you look at the back of the package, there's a little window opening, and that window opening is a conductor, and that conductor is where you bond your chip. So I bond my chip, or die in package terminology, to the exposed paddle using a conductive glue, right? And so now current can actually flow, so this grounds my entire substrate. It's something we'll talk about later when we talk about substrate coupling. But it also provides, even if I don't use a conductive glue, regardless of that, it provides a very nice way to bring ground out from my chip. So instead of going through this long bond wire lead via, I go directly short bond wire, it's called a down bond, into this huge conductive plane, and then through a via to my ground plane. And I don't have to do this just once. I can do this several times, right? I can have, if I want, 10 or 20 ground connections, and each ground connection will reduce my ground inductance. Not quite linearly as you would hope, because they're mutually coupled, but considerably enough. Okay. Another option is to use what's called flip chip technology. And in flip chip technology, what we do is we don't use bond wires at all. We say, you know, this is the source of a lot of problem, these big leads, these bond wires. Let's just flip our chip. So what we do is we rotate it. So this is the bottom, this is the top. And we use bumps, solder bumps, to bond our chip to a package. Okay? And this is our substrate. So this is our package substrate. So it's almost like putting our chip inside a bigger chip. And the second chip can be made of many different materials. It could be FR4, what you're used to, with the same material as the board itself. It could be ceramic. It could be low temperature co-fired ceramic, what's called LTCC. And you know, basically, this lots of different materials have different thermal characteristics. And the nice thing now is that I don't have to just put my pads on the ends of the chip, right? Now I can actually have pads all over the chip. I can have a grid. So if this is my chip, I can have a grid of pads, and each one has a bump, and they all go into this package. And so now I can have, first of all, a capability of having a lot more leads than I could in this technology. And also these bumps and vias can have very low inductance. Just to give you an order of magnitude, you know, this again, roughly speaking, is on the order of nanohenries. This can be on the order of 50 to 100 picohenries. So at least a factor of 10 better in terms of inductance. But of course it costs more. The other problem with the flip chip technology, if something goes wrong in your chip, there's no way to probe it directly, right? In this technology, you can always put probes onto the surface of the chip and try to figure out what's going on. Here, once you flip the chip, it's inaccessible, right? That's another advantage of this technology over this.
Heatsink?
Yeah, heatsink, exactly. Why don't you explain a little more?
So, the first technology that he can go from the top, and this, when you flip it over, he cannot go from top.
I think by top you probably mean bottom. Okay. Yeah. So in this technology, silicon is a good conductor. It's also a good thermal conductor. So I can actually pull heat out through the bottom of the chip. So, and there's going to, you know, this is usually covered up, and the plastic on top is not as good of a thermal conductor. So there's not as much convection. So there's some convection, and there's mostly conduction. So most of the heat is being removed through conduction. Some of it's also being removed through these wires and being pulled out, right? But most of it is going through this bulk substrate. The substrate is physically large, and then this package is also physically large. So this acts like a good heat sink and pulls out the pulls out the heat and keeps the temperature low. Over here, even though I have this nice conductive silicon, it doesn't make thermal contact on this side, right? So there's no thermal contact. So the only way to lose heat here is through, let's say, convection or radiation loss. Most of the heat has to be pulled out through these vias, and maybe some of it through this package. And so this die will run hotter than this die over here. Okay. questions or comments? Okay, how about signaling, right? And so we talk about packages, but a lot of times we have to have chips talking to each other. And moreover, we have to have, even on chip, distances are getting large enough because the frequencies are getting high enough that sometimes we have to worry about intra-chip communication. And so here we have several different options. And of course, if you're in the lab, it might just be convenient to hook a wire like this, right, if you're doing some prototyping. But clearly a wire is not really a good solution because it has lots of inductance, just like we talked about before. So one way to reduce the inductance is through a structure like a twisted pair, right? And as you know, twisted pairs are very popular for long-range communication. We use them in phones, use them for data communication. Why is a twisted pair so much better than just two wires next together, right? So I could take a wire 1, wire 2, put them relatively close together, or I can do this twisted pair thing. Okay. So why is it that you cut your phone wire and you look inside, it's like this, not like this? Okay, Christian?
If you twist them together, you keep them as close as possible, which is 2 radii away.
Okay, that's one reason. But let's say I just stick these together. I can do that. I can make these wires basically physically touch each other. And then I have the same spacing.
Well, in power lines, they twist them like that to cut down on the mutual inductance between the two.
How does that cut down mutual inductance? I mean, the mutual inductance between these two wires is part of the wire, right? It's something that you can't really... The mutual inductance between these wires is the self-inductance, right? What we're calling self-inductance. What you're saying is that if I have another wire here and I'm routing two different signals, your claim is that these two wires will couple more than two pairs of twisted pairs, right? Okay. Why is that? Okay. Anybody? Yes, Vincent?
Was it because of the loop they kind of cancel each other out, or the in the opposite phase?
Yeah, very good. Just like that common mode cancellation technique. Here, I'm defining loops, and these loops are constantly twisting, right? And so you can imagine the loop here, and it slowly twists, and then a little bit later, it appears now with opposite polarity. So this guy and this guy cancel out. This person and this person cancel out, and so on and so on. And so, you know, these loops eventually flip polarity and they cancel each other out. So this is plus, minus. Then you just shift over and the same thing happens here. Shift over and the same thing happens here. Right? So twisted pairs are pretty nice for that reason. We don't use them much, though, if you're talking about building a board. First of all, because you don't want to use wires, right? They're not as reliable as traces on your PCB. Usually we use microstrips, right? We use basically transmission lines between here and the ground plane. So this is the ground plane. And this is our signal line. So why use a microstrip as opposed to two wires that are just close together? So let me maybe draw a picture and make it a little more clear. So I have kind of a chip 1 here and a chip 2. And I have a couple of options. One, I can route signal and ground together like this. Or I could route... And, let's say that, okay, that's fine, but let's say now I have something like this. And let's say that I decide to use the same ground because my board is kind of messy. I don't have a place. Well, obviously this is a bad idea, right? Because this is fine, right? This has a small cross section and it picks up little noise, but this loop now has a huge cross section and it can pick up noise. Besides noise, what else should I be concerned about?
Impedance matching, like
Why is that important?
at high frequencies you see reflections maybe.
Yeah, very good. So in this line there's a characteristic impedance, right? And it's determined by the spacing between these two wires. And if this structure is on the order of the wavelength, then I'm going to get transmission line effects. So if I send a signal on this end, let's say some data, when it reaches this end, if it doesn't see an impedance match, it actually will reflect. And that reflection will, so at any given time, I'll be receiving a signal plus a signal that went back and reflected. And so I get intersymbol interference. On the other hand, if I match these lines, the reflections go away and everything is nice. And the nice thing about using a microstrip transmission line is that it's a very well-defined impedance. So I can tell the board manufacturer that make the width of this wire just right to get 50 ohms or 75 ohms or 200 ohms, whatever I need. And that will form a transmission line with my ground plane. And no matter how I route that, I don't even have to now worry about what it looks like. Just automatically, the physics tells me that the current, the return current, will flow right under, more or less right under that signal line at high frequencies. At high frequencies. At low frequencies it goes everywhere. But at high frequencies it will follow my conductors everywhere. And this is why it's so important not to have cuts in your ground plane. Because if you inadvertently, let's say you decide, oh, you know what, I've got to put a hole here because I need to have a via go through. All of a sudden this current can't go directly under the conductor, and let's say this hole is really large. So now this current is forced to go around. And what happens? I've created another loop, and I can pick up interference and transmit interference through this loop. Okay? So watch your ground planes when you do microstrip transmission lines. Okay, the other way to the other thing to consider is when you design circuits and you're worried about coupling, there's two kinds of coupling that you would worry about. One is, well, there's actually many kinds, but let's talk about two kinds for now. There's electrical coupling, and it's very obvious. Electrical coupling is just capacitive coupling. So in theory, everything is capacitively coupled to everything else. If you build a board, every piece of wire is capacitively coupled to every other piece of wire, right? No matter how far you put them away, they're still coupled. And there's a couple of ways to reduce that coupling. One is we just shield our signal lines, right? If I have a sensitive signal going through here, I don't want to pick up any noise, so I put a shield around it. And now, if this shield completely surrounds the signal line, then all the field lines terminate on the shield. And so if I have positive charges here, the negative charges on the shield just balance these positive charges, and no charge is induced on my signal line, right? Another way to do it is, again, this ground plane that we just talked about. This ground plane is much closer to your signal than, let's say, this far away signal. So most of the field lines here would terminate on the ground plane as opposed to on a far away conductor. So the fact that I have this ground plane everywhere, in effect, acts like a shield. It improves my isolation between structures. Okay, questions about that? Well, I have to be careful, because if I don't ground my ground plane, so-called ground plane, then things can actually get worse. So before I had this far away coupling, which was maybe 1 femtofarads. And now I have this ground plane that effectively has, let's say this capacitance is 100 femtofarads. And let's say it's a low resistance ground plane, so this is a few ohms. So now instead of having 1 femtofarad of coupling, I've got 100 femtofarads in series with 100 femtofarads, or 50 femtofarads. So now the coupling is 50 times larger. So be careful, put in that ground on your ground plane. Make sure it's well grounded at multiple points. So that's the one kind of coupling we have to worry about. The other kind of coupling, static coupling, in other words, low frequency coupling, is magnetic coupling. And we've talked about this already a lot. We know that it's really defined by the size of the loop, right? So in the package, we try to minimize the loop by using adjacent leads, for instance. The smaller this loop, the smaller the pickup, the smaller this loop, the smaller the transmission. Okay? Can I use shielding with magnetic fields? Does this help? Anyone want to take a guess? I've got a shield, I've grounded it, and then I run a sensitive signal through there. And this sensitive signal, I'm trying to prevent that from picking up the magnetic flux of this loop.
I'm going to guess no.
All right, good guess. Why not?
Because the loop is still there. I mean, the magnetic still goes through the loop.
Yeah, you're absolutely right. Nothing has changed. I've still got this loop here, and it picks up, right? It picks up nearly the same flux as before. Maybe a fraction of a percent less because, this material here changes the loop a little bit. But for the most part, problem is exactly the same. In fact, because this shield is an open structure, it's just a piece of wire, right, effectively, there's no current flowing on the shield. There's no induced current on the shield. And so the shield can't do anything. The way to make the shield work, well, actually, how can I fix that problem? What's an easy fix?
To make the loop smaller, much smaller.
How can I do that?
Because I saw the picture.
Well, what can I do to the shield to make it work?
Put it around the loop itself.
So you're saying do a big shield like this.
Or move the line into the shield.
Now this won't work either.
Move the line up into the shield. Together.
Well, actually, this work. No, this still. I guess this could work. This potentially could work. But the idea is I need to ground the shield at 2 points. Instead of just grounding it in the middle, I ground it at both ends. And the reason that works is now current can flow in my shield, right? And so the current that flows in the shield is exactly the noise current that I would have picked up. But the shield current produces a flux in the opposite direction as this incoming flux. So this loop is in the opposite direction here, and it precisely balances out. Almost, if the shield had zero resistance, then this current would produce a magnetic flux that would cancel out the flux of this current. And so here I would pick up no noise. The idea is that because this shield forms a closed loop with zero resistance, current will flow, induced current will flow just enough to balance the incoming magnetic field. Okay? Now there's even a simpler way of looking at this, if you don't like this explanation. Another way to look at this equivalently is I've reduced my loop area. So instead of having current flow in this big loop, now current flows through the wire just like before, and then through this ground. Oops, I drew it wrong. Then through this ground, then through the load, then through the ground, and then through the shield. And then through the ground again, and then back here. So what's happened is instead of having this huge loop, I've got this tiny loop. And that tiny loop picks up less flux. Okay, that makes sense to everybody? Okay. So this is in fact why it's actually smart sometimes to avoid too many ground connections. Because what you can see here is, let's look at three cases. Of course, this is the worst case, right? There's no shielding at all. So here, I do the smart thing and I put in a shield, and then instead of grounding both ends, I just ground one end. On the other end, I just connect the negative terminal of my load directly to the shield. And so I ground the load through the shield. Now this is the only loop, right? But over here, I actually have two loops. I've got this long big loop, and I've got in parallel with it the smaller loop. So this is the big loop, and then this is the small loop. And they're both active. And you know current takes the path of least impedance. So at low frequencies, current will take the big loop. And now I have a source of magnetic coupling at low frequencies. So it's better to actually do this case B here and only ground one end. Okay, and this is again the same idea. What happens is that there's this shield current that flows. In the case where I have two grounds, I get my shield current. Unfortunately, because the shield has resistance, I don't get perfect cancellation, but nevertheless I get the shield current which cancels the flux of the noise. But also I've created a big loop here, and this big loop can pick up noise. And here I see a noise current flowing in the shield current. If I take this connection away, that would stop the shield current from flowing. Okay? Well, this is one reason to go with the triax wire. Right? Have you ever gone in the lab? Who's worked with triax cables? Oh, you will. So triax is, coax is you have a signal conductor and a ground around it, right? Triax is you have two grounds. So you have your signal conductor, ground 1, ground 2. And the idea is that the triax current is the big loop. The outer shield forms a big loop where noise currents can flow. The inner conductor here is where our return current flows. That keeps our loop small. So this first loop is a small loop, and that picks up very little noise. This big loop, which is the triax loop, is where our noise current flows. If we didn't have this triax loop, the noise current would flow on our shield. And because the shield has resistance, it would form a parasitic signal, if you will. It would be a noise signal. But because this triax signal now is not connected to our load or to our input of our amplifier, you will not have noise pickup. Okay? That's a little bit of a subtle point. Think about it. Come to office hours if you're having trouble seeing that. The fact of the matter is, though, that if you build things, you're going to end up with multiple grounds. It's just unavoidable, right? You'd like to just have one ground point and then very well controlled ground connections to everything else, but in reality, you're going to have situations where either you're working with someone else's board where they've got multiple ground connections, or you just have to make multiple ground connections. And whenever you have multiple ground connections, always be aware that there's all these loops in your ground unintentional loops that are picking up noise. And one way to model that is to draw two different ground symbols to distinguish the fact that ground here is not the same as ground here. There's actually a noise voltage between them. This noise voltage is the induced currents that are flowing in your ground loops that are producing noise. Okay? So now we can see that in this amplifier, the input voltage between here is not just our source voltage, but in series with it, we've got noise. So whatever ground noise we pick up is amplified by this amplifier. So if you're trying to do a very precise A to D converter, and this is your first stage amplifier, and you have no idea what's going on, there's all this noise being amplified. And where is it coming from? It's coming from your ground loops. Okay? So how do we get around that? Well, one option is to use a transformer. And what the transformer does is, if you look at now the voltage at the input of the amplifier, it's the voltage across the secondary of this transformer. The voltage across the secondary is some factor times the voltage across the primary. And you can see that this loop is independent of this ground noise, and this loop is independent of this ground noise. So this ground noise, even though it can move this point up and down, we don't care because that also moves this point up and down. What we care about is this differential signal. In other words, we've turned the ground noise into a common mode signal. And if this amplifier has good common mode rejection, we've gotten rid of the noise. Well, we can also go fully differential, right? Let's zoom in on this plot here. So now I have a fully differential amplifier, and instead of bringing in just signal and ground, I bring in two signals, and ground is intrinsically connected to my amplifier, but hopefully my amplifier is not sensitive to common mode noise, right? It has supply rejection, right? Should have ground rejection. So in general, I can just call this PSSR. Power supply, PSSRR. Rejection ratio. So this signal is going to get rejected hopefully by 30, 40 dB even at high frequencies. Low frequencies, a lot more than that. 50, 60, 100 dB maybe in a good design, good balanced design. So the ground signal and the VDD signal, they all get rejected, and so our ground noise, which is really the same as our supply noise, it's not the same, but the same thing applies, is now rejected by the common mode of the amplifier. If we don't have a fully differential source, right, then we can create one again with a balun. So here we have our signal source. We go through a balun and create a fully differential signal. And again, our common mode ground noise is rejected. Here's a question for you guys. What's really the advantage of using a balun? Why couldn't I just take these two signals here and bring them into the amplifier? This is the differential signal, right? Not quite. I mean, this is ground, this is a signal. But if I have common mode noise, it would appear on this guy, but it wouldn't appear on this guy, right? And so that would create a differential signal. So that's not a good question. What I'm trying to get at is it's very important to have balance in your circuit. And this is a picture that shows why. So in this particular example, I have a differential amplifier, and I have my source, and instead of just connecting this point to ground, in which case this would be in series, I do something smart. I take this all the way out and connect it at this point. So now the ground noise is a common mode noise, right? So the ground noise moves this node up and down and this node up and down together, and the amplifier rejects the common mode noise. Is that right? What's the flaw? Christian?
There's a source resistance, so it's going to change, right?
Very good. So the source resistance actually changes the picture. So if I think about this voltage source, what noise does it induce on this loop? Then this loop goes through the input, comes back to the ground and through here, and it sees this source resistance. This might be a kiloohms. On the other hand, through the second terminal, it goes to ground and comes back without any resistance. And so in fact, it's not going to create a balanced noise signal. It's probably going to create more noise in the negative terminal because there's less resistance. That's why I use this circuit, because now in either direction, this direction and this direction, I see the same impedance. I take the single-ended source and create a differential resistance. I create a differential source. And so now I'm equivalent to this picture, and the noise induced on this loop is the same as the noise induced on this loop. Okay? Questions or comments? All right. So that takes care of package coupling, supply coupling, coupling through your leads. It gives you a good idea what to do to take care of your ground connections. But at the end of the day, you do all that stuff, and you still have your nasty substrate, right? So we've got to live with, you do all this good stuff on the outside, and you cut down the noise, but ultimately, all your circuits are sitting on the same substrate. And it's kind of odd that every circuit you build is coupled to the substrate. And the substrate is a piece of conductor. And so the substrate creates a resistance between every two circuits on your chip. Right? So in this example here, you've got digital circuits that are all creating noise. That's getting somehow injected into the substrate. Currents can flow in the substrate. They get picked up by your analog circuits. So even if we're not talking about the supply, noise on the supply, noise can get through the substrate and get to sensitive analog circuits, and vice versa. So if I've got a really big power amplifier on here that's putting out a watt of power, that produces bounce that also bounces the substrate around, and that creates substrate currents that go back and interfere potentially with our digital circuits. So it's a two-way street. What's the mechanism of substrate injection? Well, as I mentioned before, everything is coupled to everything, right? The substrate is a conductor. So effectively, it's a distributed resistor. You can think of it as a distributed resistance network. Right? And of course, this is a lattice, discrete lattice. It's a continuous lattice. So between any 2 points in the substrate, there is a resistance. And a typical way that you see substrate injection is you have here an NMOS device, and we have basically a ground connection that is basically ohmically contacting the substrate. And so as this device pulls current into and out of the ground node, because of ground inductance, I get bounce on this node. And this bounce is directly injected into the substrate, and it can get picked up by another device. So in this case, the signal that's bouncing up and down, this current can go through this capacitance, right? This is a reverse bias junction, but it has capacitance. So at high frequency, the current goes through this capacitance. This is a well. A well might be physically large, so you pick up that signal pretty easily. And then at this point, it can flow into, let's say, the P+, the drain side of a transistor. And this might be the output signal. So now I'm coupling noise from my ground to my output through the substrate. So even if I've made sure that my ground terminal and my package terminals are isolated, I still pick up noise through the substrate. Okay? And of course, don't limit yourself to just this path. Anything you put on the substrate has capacitance to substrate. If I put, let's say, a resistor, piece of polysilicon, well, that has capacitance to substrate. And that couples to the substrate. So my resistors couple. If I build a capacitor, right, it has bottom plate parasitics. Where do they go? They go to the substrate. So that couples to everything else. So not just transistors, but also passive devices easily couple to my substrate. Okay? Questions or comments?
So nowadays people start using like the triple well or the additional well to the kind of decouple two sensitive parts.
Yeah, it helps, right? It helps. So what happens is that now, instead of having this ohmic contact, I have to go through another capacitance. But it's still there, right? This might buy me 20 dB or something, but ultimately that coupling is still there.
Is there a take on, say I have a digital part and analog part on the chip, which one do you usually put in the extra well? Is there like a difference in doing so?
Yeah, usually you would put your analog in the extra well because the extra well takes up more area. So if you want to design your digital circuits with the extra well, it automatically gets bigger, and you presumably have hundreds of thousands of gates. So you want to keep your digital as small as possible. So you could put all your digital in the substrate and then put your sensitive analog far away and in its own well to help things. If you want the maximum isolation, you put both in the triple well. All right, when you lay down transistors, you always remember there's a fourth terminal, right? That's the body of your transistor. And really that's how that's the body of the transistor is either resistively connected to the substrate or capacitively connected to the substrate through the well capacitance. And the way you make contact to the body is through your source-drain junctions, right? You might think of these are external to your transistor. They're not really necessary, but they're just there, unfortunately. So every junction is capacitively isolated from the body, and the body is also connected to the substrate. So keep in mind that your transistors are coupled to the substrate. Unfortunately, when you do simulations, most of the time we just ground this terminal, right? And so there's no coupling that occurs from device to device. But if you really want to be careful, in an ideal world, you would take every body terminal and it would go into this black box. And this black box would be this huge resistive network that would connect every body to every other body, right? And that way you could simulate substrate coupling. Unfortunately, your SPICE circuit with 10 transistors would turn into a SPICE circuit with 10 transistors and 100 million resistors. And, it would basically take 10 weeks to simulate. So doing a brute force approach of having a substrate doesn't work. You have to do something more clever. It's also important to ask yourself, what kind of substrate am I using? We're not used to asking this question. But it's very important to know the resistivity of your substrate. And there's 3 standard flavors for bulk CMOS. So bulk CMOS comes in kind of like vanilla CMOS. People might call it bulk CMOS, where the substrate resistivity is on the order of 10 ohm centimeter. That might be a little more, a little less, 10 to 100 down to 1. So maybe 1 to 100 is a typical range. Of course, that's controlled by the doping. And then you might have a surface layer that's a little bit different conductivity. This is where your well is. So this might be your well, your N well and your P well. And because the N well and P well are doped on top, they end up being a little more conductive, right? You might have what's called an epi process. An epi process for a time was really popular. When I was a grad student, it was all the rage. And it has a lot of problems for analog design. It's great for digital design, but it has problems for analog design. The idea behind an epi substrate, first of all, it's more expensive because it's heavily doped. So it's heavily doped, so it's actually fairly conductive. So here we see it's about 10,000 times more, 1,000 to 10,000 times more conductive than a regular bulk substrate. And because you can't build transistors in the body, you have to have a layer which is called the epi layer, epitaxially grown, that has the same conductivity of, let's say, the bulk here. And this is where you're going to form your transistors. So why is this good for digital? Why did people even use this if it's more expensive? Any ideas?
Because the silicon bar is a heavy dope, so the capacitance, actually capacitance is larger.
Yeah, it doesn't help with capacitance. There aren't that many times when you think about the substrate, right? What's one instance where you have to worry about substrate currents?
Latch up?
Yeah, latch up. So who here has heard of latch up before? Okay, so you guys have heard of latch up. If currents flow in the substrate, right, you get resistive drops, and those resistive voltage drops could potentially turn on and off junctions. If those junctions turn on and you start injecting minority currents into the substrate, you get latch up. And we'll talk about that a little bit next lecture. So this is very good for preventing latch up. Unfortunately, we'll see it's very bad for substrate coupling. It's also very bad for RF circuits because eddy currents can flow here and reduce the quality factor of our components. The last case, almost an academic case, is what's called a undoped substrate. Well, it's really doped, right? It's hard to get a pure substrate, but it's very resistive. It's on the order of kiloohms to tens of kiloohms resistivity. You can buy these, again, I believe they're more expensive. But because of the danger of latch up, they're not used at all if you're doing a real process with digital circuitry on it. But it's great for substrate isolation because if you think of this as a resistor, this is a dead short practically, right? This shorts every node of the circuit to every other node. This one has a resistance between each nodes. This one's almost an open circuit, so it's mostly capacitive coupling between different nodes in the circuit. And so this is the best for substrate isolation, but it's not used. You might see an academic paper here and there, but it's not used. Now, if we talk about other technologies other than CMOS, like SOI, then you actually can use this. There's no reason, because this substrate is electrically isolated from your transistors anyway, and so you don't really care. Other technologies, silicon on sapphire, again, same thing. You can use a very highly... This is just now a mechanical support for your circuits, and so the electrical properties you can design to suit your needs, and you can make this very resistive and reduce the coupling. Okay. I think I'm going to stop here. We still have 15 minutes. We're going to have our review. So I'll continue this discussion on Thursday.